Hello everyone and welcome back to Introduction to Number Theory. This time we'll talk about linear Diophantine equations in two unknowns. Well, a Diophantine equation is simply an equation which needs to be solved within the set of integers. A linear Diophantine equation is an equation where all the unknowns, x, y, z, and so on, are with degree 1, with power 1. So here we see an example of a linear Diophantine equation, and a, b, and c are just some integers. They are known, but we denote them using letters in order to perform some general conclusions. And x and y are unknowns. So all five letters denote integers. Suppose we have a particular solution of this equation. Say x equal to x0 and y equal to y0. In some time, we will see that some of linear Diophantine equations have integer solutions, some don't. But now we need to answer the question, what is the structure of all the solutions? And the answer is the following. If we take a particular solution, then all of the solutions of this equation are given by formula x is equal to x0 minus bt, y is equal to y0 plus a t. But this is not completely correct. And this is a standard mistake which is made by many of those that study number theory. These formula work only if a and b are mutually prime. And this is a very important condition. So please pay attention. Well, if a and b are mutually prime, then the set of all solutions is given by this formula, and t is an arbitrary integer parameter, which means that if we substitute t with any integer number, we will receive a solution for this equation. And on the other hand, any solution of this equation can be represented in such form where t is some integer. Now let's prove that this is so. Let's prove this statement. So we have a particular solution, x0, y0, and take just any other solution, say x1 and y1. So a x0 plus b y0 is equal to c, and at the same time a x1 plus b y1 is equal to c. So we subtract one equation from another and see that a multiplied by x1 minus x0 plus b multiplied by y1 minus y0 is equal to 0. Thus, we see that a multiplied by x1 minus x0 is divisible by b. However, as we know, a and b are mutually prime. So since a and b are mutually prime, then from this it follows that x1 minus x0 must be divisible by b. Then denote x1 minus x0, say that it is equal to b multiplied by some t, where t is an integer. And we could do the same thing with the second summand and say that it is divisible by a, and then y1 minus y0 must be divisible by a. But then we would get some other integer parameters. So we better substitute this equality. We use this equality and substitute x1 minus x0 into this equality, and obtain that a multiplied by bt plus b multiplied by y1 minus y0 is equal to 0. So from here we see that y1 minus y0 is equal to minus a t. Finally, we see that x1 is equal to x0 plus bt, and y1 is equal to y0 minus a t. Comparing this formula with the initial ones, you might say that this wasn't what we are going to prove. These formula are not the formula we were supposed to prove, because here we see minus and here we see plus, and at the same time here we see plus and here we see minus. But these formula are essentially the same, because t over here is an arbitrary integer, and also t over here is an arbitrary integer. So we can obtain one pair of formula from another by substituting t with minus t. And since t is an integer, it doesn't change anything. So you can write it this way, or you can write it this way. It really doesn't matter. What matters is that a and b should be really mutually prime in order for this formula to hold. Now let me just show you an example how you can solve linear Diophantine equations with two unknowns. Take an equation, say 3x plus 5y equal to 7. So first you need to find a particular solution. And simply write it. X equal to, well, for instance, we can take x equal to 4 and y equal to minus 1. And then we simply take the coefficient upon y into the formula for x and write, well, use this formula, 4 plus 5t, and take the coefficient upon x into the formula for y and use another sign, minus 1 minus 3t. Well, since 3 and 5 are indeed mutually prime, then this is a proper way to find a solution. Write that t is an arbitrary integer, and we have a solution for your initial Diophantine equation. Finally, let me notice that if we have at least one solution of such an equation, then we have infinitely many solutions of this equation given by such formula. And we can use any of these solutions for x0 and y0. So when you take x0 and y0, it should be any particular solution, and you have infinitely many of those. So pick any and write the formula.